All right, good afternoon, everybody. Morning, I guess, still, right? Feels like a long day to me. Homework 9 is due on Wednesday, and you're going to be using specific energy analysis for that assignment. So we'll go over some examples today that'll help you with that, and then also on Monday there will be some additional information. There's 3 problems on that assignment. The other thing that's on your plate right now is phase 2 of the design project, which is using water gems in order to size the pipe network. So we've done a couple of in-class demos to familiarize you with that software. I'm going to show you how to bring up a map in the background today so that you can draw your pipe network on top of a map that's scaled, and then the lengths are accurate and you don't have to do any user-defined lengths. What you'll submit for that draft submission on Friday of next week is just 2 PDF files and nothing else. It's going to be a PDF file that has the network under full flow, so like the demand being the design demand, and then the same network, same pipe sizes, but with no water being drawn through the outlets. So just to see what the pressures look like under static conditions. So I'll show you some additional information about that in just a minute when we do the image importing demo for water gems. So we're still in chapter 12 of the book, where we're doing total energy, specific energy, and some things related to critical flow. So any schedule or announcement questions before we look at how to import images in water gems? If not, let me just make sure that this recording's going. All right. So here's water gems, and there are 2 things that I've encouraged you to check every time you start up water gems. The first being that the units are set to SI, the other being that the friction method is set to the Darcy-Weisbach. And so to do that, if we just start a new hydraulic model, then to check units, it's under the Tools tab. Just wait a moment. It's setting up all of the databases and so on that we will be drawing on as we run the simulation. It's usually not quite this slow. I'm not sure what the case is. All right, so Tools, More, Options, Units. Okay, set to SI, so I'm good there. And then the other thing I would check just at the beginning, anytime I start a new project, is to make sure that I'm on Darcy-Weisbach. So that's under the Home tab, Options, Base Calculation Options, double-click that. It's on Hayes and Williams, and so I'd switch it over to Darcy-Weisbach. Okay. So now, on the left side, there's this background layers, and you already know about this window, which is for annotation. And the demo that we worked previously went into some considerable detail on annotation, and so you should watch that again if you need to be reminded of how to do annotations. But this window, you would select New, File, and then what we're going to do is browse to the location of the TIFF file. Now, right now it's available in Blackboard, so you'll need to store it on your computer somewhere. You know, store it on your local machine. I've got it here. It is the file that's called Scaled Map Import to WaterCAD. So it's a .tif file. It's not big. It's only 1 megabyte. When you hover the cursor over that, you can see what its dimensions are. It's 4250 pixels wide and 2750 pixels tall. So that's just how many dots there are comprising the image. And I've set this image up so that 1 pixel equals 1 meter. So when you select the file and click on Open, it's going to come to a menu, like an image importing menu, where you're given options related to scaling. And so it's asking, you know, the bottom left part of the image, where should it be set in the program's coordinate system? Because down here at the bottom, if you move your cursor around, the cursor has locations in terms of its x value and y value. So x and y coordinates. And so here, when you import the image, you're just telling it where to put the image in your system's coordinates. And you can just use the default. There's nothing that needs to be changed there. But very important, turn off use compression and turn off optimal image loading mode. I'm not sure what those do, but they crash the computer in most cases. So I don't know why that would be the optimal image loading mode, but maybe it's for different file formats like .png or .jpeg, but whatever the case may be, if these are turned on, then your TIFF file is not going to load into the background. It would probably just kill your program. So turn it off and then click OK, and what we'll see is just this weird little edge. So zoom out using this zoom extents, and now here's the whole project map. And what we can do is we can draw a layout, a network layout on top of that. So maybe starting with my reservoir, I'm going to put the reservoir up on the hill someplace, and now I'm switching over to junction, and I'm dropping these wherever I know that there's junctions. This wouldn't be a very good pipe network because it's a pretty indirect route that I'm taking, right? We might be able to do better than, I can turn this off and look at it. That's probably not the minimum pipe length, but the point is all of these locations that I've drawn, those are scaled pipes. And so just to prove it, let me draw on here. Here I'm going to put one outlet there and one here. And if I open up that pipe and look at its length properties, it's going to tell me that the length of that pipe that I just drew is 100 meters. So that's the advantage of having the map in the background, is that wherever you draw pipes, they're going to have the actual length that they're supposed to have in reality. As long as we bring this image in as 1 pixel equals 1 meter, which is just those default import options. So that kind of drawing the line on top of the scale confirms for me that 100 meters in this pipe length is correct with the reality that's described by the map. Okay, so I can zoom back out again, turn this off. Now, what I don't like is that the annotations and the symbols are super small right now. And I can change that if I expand, for example, the pipe label size by editing the existing annotations with an increased scaling. Right now the whole height multiplier is 1. If I change that to 20 and apply, now I'm starting to actually see the pipe sizes, or the pipe labels. Okay, so you can make those adjustments. Same thing with like the junction symbols. They're a bit small right now. If I right click on the word junction and change the properties, the symbol size multiplier, let's see if I make that 15. Now I can actually see the dots that represent the junctions. Same thing right now, the junction labels are too small. So let me edit the junction labels with an increased multiplier. Now the junctions have labels. So those are the things I wanted to show you. How to bring an image in the background, and how to change the size of the annotations if the, importing that big image in the background, now suddenly the labels are too small. You can scale it. And this can be switched on and off. When you actually print your map for me, don't have it on, because it's hard to see the network details if the image is kind of cluttering up the screen. So have this switched off when you print your network map. Let's just see what that looks like right now if I do a print preview. This sometimes is a little bit of a slow process. That's not taking up all of the space. It'd probably be better if I did like a landscape orientation, I think. That's a little bit better zoomed in. The nice thing is when you print this to a PDF, I'll be able to, I'm going to do that right now. I'll print it to PDF, Microsoft Print to PDF, and it's probably going to prompt me for a location. So I want to select some place I'm going to be able to find later. I'm going to call this Water Gems Map Demo. So it's just created a PDF file that I can go and locate on my computer. And even though it's not taking up the majority of the screen, because it's a PDF, I can zoom in, and those are what we know as rasters rather than, no, they're vectors rather than rasters. That is, like, these are lines with an infinite amount of definition if we keep zooming in. It's not going to get pixelated because they're actual lines. Whereas if you did something foolish like just took a screenshot, let me try, like, what if I didn't know how to print and I just pressed the print screen button and then tried pasting that into a Word document? It's going to look terrible. Or even worse, if I took a picture of the screen with my cell phone camera, that would look terrible as well. But if you do print screen, the problem is, okay, I've pasted that, but when I zoom in, it's not as sharp as if I make it as a PDF. So the key to success here is once you've got your network map, File, Print Preview, and you can play around with the scaling. You might be able to, depending on how you've got things zoomed in, you might be able to get it to fill more of the screen. Print Preview, and then Landscape to get it to fill more, and then just print, and then choose, instead of a physical printer, print to PDF. So the two maps that I want is, what does the annotated map look like under maximum flow demand and then under static conditions. So keep in mind, you got to turn off image loading mode and compression in order to get that image into the background. And then here's an example of an annotated map. The examples that we did in class, I spent some time showing you the annotations, and the handout with the assignment description, that also tells you which annotations I need. So, you know, when all else fails, read the instructions, because the instructions will explain which annotations you need. You should have the pipe location indicated, you should have the diameter annotated, the length annotated, the flow rate through each pipe should be annotated, the pressure at a junction, the flow rate out at junctions, the reservoir elevation. All those should be annotated. And here's a student example. This is somebody from a few years ago. They did a nice job on the annotations, but back then I wasn't emphasizing so much the idea that you should optimize the pipe location. You know, nowadays I would say that that's kind of a bad design because, for example, they have water going to this location J. You know, the pipe goes from the hospital to the housing project through location J, but no water is being withdrawn at location J. So there's no reason for the pipe to be there, for the junction to be there. So an improvement would be having the water go straight from K to I. So straight line would be less length, less cost. So part of your job is to optimize the pipe diameter, but it's also to find out how could you minimize the length while still getting to all of the locations that water needs to be delivered. Another way that this pipe could be, this network could be optimized better is, look at this pipe EF. It's only carrying 5 liters per second. 5 liters per second is going from F to E. Water's also getting to E from this junction, and it's 28 liters per second. So I could probably just eliminate this pipe altogether and just have all the water getting to E through the other pipe. So that'd be another way to reduce the overall length of the network, is to eliminate redundancy. All right, that's all the time that we have to spend on the project for now, but remember, it's due a week from today. I've started grading the flow demand estimates. The few that I've done so far looked good. If I don't get to your correcting your flow demand estimates before you're finalizing your network map, that's fine. You can just go with your flow rates as you understand them now, and then if revisions need to be made later on, it's very easy for the final submission for you to modify your pipe sizes once you've got updated flow rates. So just proceed with the flow demands that you've already calculated, unless you get your comments from me early enough that you can integrate them and adjusted flow rates into your network sizing. Any questions?
Yeah, you had said before, you don't want to have dead ends in the network. Then in that, you said you...
In this one, dead ends are fine because you're only having water going to locations where water is being withdrawn. So what we're assuming is that this town, let me bring up the map of it. This town is fully built out from day one. So this isn't the case where like it's going to be some years in the future that water is actually being drawn from some of the locations. But I mean, in a real world design, if you're taking a pipeline to a neighborhood that's going to have only very low flow rates or no flow rates for quite some time, then you potentially could be, through a dead end, degrading the water quality or causing like precipitation in the pipe as iron and manganese precipitate, like clogging up the pipes. But here, we're just saying that at each of these green arrows, there definitely will be demand. And so those concerns that I talked about earlier don't apply. So you can have dead ends here. Are there any other questions? All right, well, let's move back to open channel flow. Remember that specific energy is the depth and velocity head. And velocity head we can express in terms of v squared divided by 2g or q squared divided by 2g a squared. And so if we take the derivative of specific energy with respect to depth, so that is, how is the specific energy changing with respect to depth? Look on the curve at the slope of this line. There's a certain point where this line is completely vertical. That's at the far left edge of the specific energy diagram. So where there's no slope at that location of no change in depth and with respect to specific energy, those are the critical conditions. We've already said that critical conditions are those that are associated with the least amount of specific energy for a certain flow rate. So this point furthest to the left is where we find the critical depth and the minimum specific energy. And so this is where we get the Froude number equation of saying that, you know, the Froude number is 1 at critical conditions, and we could find the depth by we could find the critical depth by setting the Froude number equal to 1. So if we rearrange this, saying at critical conditions, and put on the left-hand side the flow rate squared divided by g, and on the right-hand side putting the area when the depth is critical, and b is the top width when you have critical conditions. This is true when we have critical conditions. And so, you know, q squared times b divided by g a cubed is equal to 1 at critical. So just rearranging that algebraically gives us this expression. And regardless of whether it's rectangular or trapezoidal or semicircular or triangular, whatever the channel cross-section looks like, you could use this to calculate the critical depth. There's going to be a shortcut I'll show you later in just a few minutes that only applies when you've got a rectangular channel. This is the equation that will never lead you astray. It'll always give you the correct depth. So just an example of how we could use it is if we had a rectangular channel with a width of 4 meters and we're taking 10 cubic meters per second through here. So Q is 10 cubic meters per second. If we want to find out what is the critical depth, then Q squared divided by G is equal to A at critical depth cubed divided by B under critical conditions. And so the top width when the flow is critical, like we're trying to find out what is the critical depth here. The top width, B, is the same if you've got a little bit of water or a lot of water. So B is always 4. And Q squared would be 10 squared divided by G, 9.81, is equal to area under critical conditions. And so area is 4 times the critical depth. And then we got to cube that. And then B sub C is 4 meters. So we can find the critical depth here. 10 squared is 100 divided by 9.81 times 4. And that's equal to 64. I think 4 to the third is 64. Let me just get my notes here. Y sub c to the third power. So this ends up being 40.7747 is equal to 64yc cubed. And so if you find out, put it in your calculator, what is y sub c, then what we're going to get is 0.860 meters. So that's just an illustration of how that formula would give you the critical depth. For a rectangular channel, the same method would apply if it was trapezoidal. It's just that we'd have to calculate B in terms of Y. If it was a trapezoidal channel, then what the critical depth, or the critical top width is, would depend on how deep the water is at a given point. So we'll do that later, that additional complication. But that just illustrates how this formula can be used to determine the critical depth. Now, if you've got a rectangular channel, then the top width and the bottom width are always the same. And there's this new term that I'm going to introduce to you, a notion of the flow per unit width. So if you take the overall volumetric flow rate in terms of cubic meters per second, and you divide it by the bottom width of the channel, lowercase b, then Q is the flow per unit width. So like this example that we just worked, the flow per unit width would be 10 cubic meters per second divided by 4 meters. So the flow per unit width, lowercase q, is big Q divided by B. So that's 10 cubic meters per second divided by 4 meters. Okay, so that is 2.5, I think. 2.5 meters squared per second is the flow per unit width. So it's just basically saying for every meter of width, so they're saying here's a meter, here's a meter, here's a meter, here's 1 meter, how much flow on average is going through there? The reality is we know that the edge has more resistance, and so there's going to be less actual flow per unit width going through the side segments than the middle segments, but this flow per unit width doesn't have to take that into account. It's just, it's saying on average, per each meter of width, how much flow is going through there. Another way that you can calculate the flow per unit width is the velocity times the depth. And so in this example, we had calculated that the critical depth was 0.866. So if you knew the velocity, for example, the velocity here would have to be Q divided by area. So that would be 10 cubic meters per second divided by 0.866 times the depth, that is the depth, times the 4 meters of width. So you could calculate what's the flow velocity, and let me just do that really quickly, pull up the calculator. So 10 divided by 0.866 times 4 So the velocity is 2.886 meters per second. And then multiply that again by the depth. So the flow per unit width, lowercase q, is the velocity times the depth. So let's just check to see if it gives us the same flow per unit width. The velocity of 2.886 meters per second, and then the known depth of 0.866 meters. So that gives us 2.5 meters squared per second. And let's see, does the units make sense? If we've got meters per second and multiply it by the depth, we do get meters squared per second. So meters squared per second is the same thing as cubic meters per second per meter of width. So how many cubic meters per second per meter of width is the same as meters squared per second? It's the same. Okay, so if you know the flow per unit width, then you can calculate the critical depth, but this only works for a rectangular section. So I'll give you an exam question that's a trapezoidal channel, and I'll ask you to calculate the critical depth. And unfortunately, some people are going to try and use this equation, and it'll give you the wrong answer. Because this equation only works if it's a rectangular channel. But if you use this formula for a trapezoidal channel or a circular channel, then it won't give you the actual critical depth, because this formula only works when big B, top width, is equal to lowercase b, bottom width. It only works when it's a rectangular channel. But if you do have a rectangular channel, then it's easy to calculate the critical depth. So for this example that we've been looking at of 10 cubic meters per second going through a rectangular channel, we know the flow per unit width is 2.5 meters squared per second. So for 2.5 meters squared per second, then y sub c is flow per unit width squared divided by g to the 1/3 power. So let's just see, if we square 2.5, that gives us 6.25. So 6.25 meters, let's see, it would be meters to the 4th divided by second squared. And then we divide it by g, which is 9.81 meters per second squared. So that's going to be units of meters to the 3rd, and then we're taking it to the 1/3 power. So let's do 6.25 divided by 9.81, and then to the 1/3 power. And lo and behold, it gives us the same 0.860 meters of depth that we had earlier determined from the full formula for calculating what's the critical depth. So that's how you can find the critical depth if you've got a rectangular channel or if you've got any shape at all. You can use either of those approaches. This one only applies for rectangular. This formula applies regardless of the shape. So any questions about that? Sometimes you'll be asked to find the critical slope. So to calculate the critical slope, we would use both Manning's equation and the geometry that's specified here. So in this problem, we know the bottom width is 3 meters, the flow rate is 186 cubic meters per second, and then we've got 1.5 horizontal to 1 vertical. And so that makes T 1.5 in that example. So let me show you these calculations so that we save some additional time to work on the specific energy analysis. But how could we find out what's the critical slope in an example like this? The process is that here we've got a bottom width of 3. We're trying to find out what is going to be the depth under those conditions. They don't tell us the depth, they tell us the flow rate. And so we're going to say what would be the critical depth by using both setting the Froude number equal to 1 and then putting it into later the Manning's equation. So this is rearranging the Manning's equation in terms of slope. So the first step is use this formula to find out what is the critical depth. So the Froude number is equal to 1, so we have to express the flow rate squared, so 186 cubic meters per second squared. Now T, or capital B, is the top width. So what is the top width when you've got the critical depth? For a section like this, which is trapezoidal, then the top width is going to be 3. So the top part is 3 plus then the side, the top sections on the left side and the right side. So there's going to be 1.5 units of length across the left side for every meter of depth, and the same thing on the right side. So here in this equation, what it's saying is it is 3, which is the bottom width component of the top width, and then 2, because there's the left side and the right side, of 1.5 times the depth. So this together is basically saying how wide is it on the combined distance of this left side and the right side. So we've expressed B in terms of Y, and then G is 9.81, and then area cubed. So area, if we go back to table 10.1 in the text, we remember that area is B plus TY times Y. So then B, the bottom width, plus T, which is 1.5 times Y, and then cube that. So setting it all equal to 1, if you put it into your solver, the only unknown here is the depth. And so the depth will be 4.121 meters. So that's the depth that you'd have to have for critical depth. But the problem isn't asking what's the critical depth, it's asking what's the critical slope. So now that we know the critical depth, we put it into Manning's equation and rearrange Manning's equation to solve for the only unknown, which is S. Because at this point we know the flow rate, the N value, the area, the wetted perimeter, because both the depth, the width, the side slopes, all of it's defined. And we have these values that come from table 10.1 about a trapezoidal shape. So the only unknown is going to be slope. So you can just put it into your numerical solver directly, or you could rearrange Manning's equation to solve for S. So here's just rearranging that formula to solve in terms of the slope. And then when you put in the wetted perimeter, the area, hydraulic radius, then it turns out that what you'd need is a slope of 0.15% to cause that critical depth. So that's how steep the channel would need to be to induce the critical depth, and so we call that the critical slope. It's the critical slope is whatever slope's needed to cause critical flow, the critical depth, so that the Froude number is 1. And any slope steeper than that would make the Froude number greater than 1. It would cause a depth that's less than the critical depth. Or any slope that is more shallow, in other words, any slope less than 0.15% would cause subcritical flow conditions. And so subcritical flow is associated with a depth that's greater than the critical depth. So the key to calculating the critical slope is to find out the critical depth and then put that into Manning's equation and solve for S. Any questions about that approach? Okay, so in a specific energy diagram, this is for a certain flow rate and a certain channel width, And there could be a variety of slopes that cause a variety of depths. And so each one of these different depth possibilities is on the same specific energy diagram, but they have different specific energies. So a certain flow rate, a certain channel roughness, and a certain channel width, but each different depth, which is associated with a specific slope that caused that depth, has a different amount of specific energy. So what if, though, you've got the water that's flowing along and it's steady and uniform, but then the water steps down. There's a sudden drop in the bed. What it's going to do is it's going to change the depth downstream. It's not going to be the same as the upstream depth was. So here where it's labeling Y1, that is the depth prior to the step down, and Y2 is the new depth after some additional specific energy has been gained. Because what happens when the water is flowing along and then goes off that step, suddenly the water has more energy. Because when it suddenly drops down by delta Z, now there's additional specific energy, and so the water is going to be at a different depth than it was before. By the way, just looking at this diagram, can you tell whether the flow at location 1 is supercritical or subcritical? No. What you need to do is compare the flow depths to the critical depth. And remember that supercritical flow is when the velocity is high, but the depth is low. Subcritical flow is when the velocity is low and the depth is high. So here at location 1, you can see this Y sub C dashed line is showing you what's the critical depth. So at location 1, the actual flow depth is greater than the critical depth. So when Y is greater than the critical depth, this is subcritical. And so what that tells us is that downstream, it's also going to be a subcritical depth. But we're going to go through the process of trying to calculate what's the new depth, and we'll have to solve a cubic equation to do that, like we have previously. In solving a cubic equation, there will be two potential roots that have the same amount of specific energy. And then the root that we'd select corresponds to the subcritical root in this case, because downstream after the step, the flow will continue to be subcritical. Okay, so this is a bed drop. And the classical thing we want to know after some sort of an obstruction or change like this is what's the new flow depth? And so what we'll be given in a problem like this is what was the initial depth upstream, and we'll calculate the Froude number upstream, or you can compare the given flow depth to the critical depth. Either of those will allow you to determine if upstream conditions were supercritical or subcritical. So you could use the Froude number or compare the given flow depth to the critical depth. So once you've determined the upstream condition, then that'll help you to know what's happening on the specific energy diagram. So here's a specific energy diagram, and let me walk you through the process of how we analyze what the new depth is going to be. Like our original depth was associated with E1. So Y1 was the original upstream depth. And so see this brown arrow that's coming over here? So we start with the original flow depth and go over onto the specific energy diagram, find the point of intersection, so right here, and then go down. So for a certain flow depth, there's a certain amount of specific energy. And you can calculate that. You know, remember E1 will just be Y1 plus Q squared divided by 2GA squared. So that's how you could numerically determine what is E1. So we found out E1. Now, because of the delta Z being a step down, you've got more specific energy. So E2 is greater than E1. So E2 equals E1 plus delta Z if you've got the water stepping down like it did here. The water gained energy because it flows over a step. It's gaining the amount of energy that was lost in elevation. So there's more energy downstream. So now we're at E2. That was this step. We go up across the specific energy diagram. There's two crossing locations. In other words, we're solving for what's the new flow depth going to be, and we choose this flow depth of the two options. The options are a supercritical depth or a subcritical depth. And downstream, the flow will continue to be subcritical, and so then we can determine the new flow depth Y2 by simply finding what was the point of reflection from E2 and the specific energy diagram. So this is a graphical way of solving the problem. You could set up a spreadsheet to solve it, or we can solve it numerically with formulas as well and find out what will be the new flow depth. So let's take a look at this case where we have 30 cubic feet per second. All right, so now all of a sudden we're in British gravitational units. Just as a reminder, if we have G in a formula, that's going to be 32.2 rather than 9.81. So at location 1, the channel is 8 feet wide, and the water was flowing at 3.5 feet of depth. And then the water steps off, it goes down 1.2 feet. We want to know what is going to be the new depth downstream in this case. In other words, what's the flow depth after the drop? So the first thing we have to do is determine whether conditions were supercritical or subcritical originally. You know, upstream at location 1, was the flow supercritical or subcritical? And so we can do that by calculating the Froude number. Let me erase some of this old stuff off of the whiteboard here. Okay, so the Froude number at location 1 is going to be the flow rate squared times the top width divided by G times A cubed, and then all of that's to the 1/2 power. Okay, so the flow rate is 30 cubic feet per second. We'll square that. The top width in the channel is 8 feet. It's rectangular, so it's going to be 8 feet of top width. G is 32.2 feet per second squared. And then our cross-sectional area, when it's 3.5 feet deep and 8 feet wide, the area there is 28 feet squared. And we have to cube that. So all of that to the 1/2 power gives us a Froude number of 0.101. So it's subcritical at location 1. So prior to the step, the flow was subcritical. That means after the step, it's going to remain subcritical, and that will help us to know which route we should select. The other way we could verify that conditions were subcritical at 1 is we could find what's the critical depth compared to the given flow depth of 3.5 feet. So for example, if I did that, Y sub C is 30 CFS, that's the flow rate, per unit width, which is 8 feet. So lowercase q squared divided by G, 32.2, and then all of that to the 1/2 power. It gives me the critical depth is 0.759 feet. And so since Y is greater than YC, then it's subcritical. So that would be another way for us to verify that conditions at location 1 were subcritical, is by comparing the flow depth of 3.5 to the critical depth of 0.76 feet.
Is it supposed to be 1/2 or 1/3 power?
It's supposed to be 1/3.
Okay.
Yep, the formula for Y sub C for the rectangular channel.
Whenever you were writing it down, you said 1/2.
Did I?
Yeah.
Yeah, it's supposed to be 1/3. Okay, so now, what is going to be the new depth downstream? So it's going to be the specific energy at 2 is, so E2 is equal to E1 plus delta Z. And so
Here's what I found.
maybe the other way to write that is E1 plus delta Z is equal to E2. Okay, so Y1 plus Q squared divided by 2GA squared at location 1 plus delta Z is equal to Y2 plus Q squared divided by 2GA2 squared. So this is the specific energy relationship that's going to allow us to find out the new unknown depth at 2. Because we know Y1, and we know all of the parameters for the area at location 1. And we know the delta Z here, it's dropping down 1.2 feet. And Y2, that's an unknown. And in A2 is Y2 times 8 feet. So let me bring up what that looks like since we're running low on time here. We're down to 1 minute remaining. So this is just summarizing those calculations from before of verifying that we have subcritical flow. And the velocity head can be expressed in terms of either flow rate or velocity head. So this becomes a cubic equation. Substituting in the flow depth at 1. Here I did it in terms of velocity. So V1 squared divided by 2G. And then here is Y2, which is unknown. And then here Q squared divided by 2GA squared. And then minus 1.2 feet. So I moved the step from being plus on the left side, then it's minus on the right side. So if you go through the process of finding the cubic equation, then it'll be y2 cubed minus 4.718 y2 squared plus 0.2184 is equal to 0. There will be 3 roots. One of which is a negative value that you throw out. The other is a supercritical root, which we don't select. So this would be the new depth downstream. 4.708 feet would be the new flow depth after the water steps off that drop. All right, we're out of time. Let me just refresh your memory that the 2 things on your to-do list for now are the homework assignment, which you could get started on, the first problem at the very least, and then the design project phase 2. So I'll see you on Monday.